So here you can see basically you can see over here that this is your ADC. Okay, so we will start the ADC. So you can see basically that in ADC what happens, your analog output voltage, it is equivalent to your digital input bits. Okay, digital input bits. So this is your digital to analog converter. So basically input over here is what we have, digital inputs that can be 0 1, and we have analog output. So this is your corresponding circuit of a weighted resistor type DAC, where you can see basically I have 2 to the power weights of resistance given. Okay, so simply I have solved over here, where this green color line, it corresponds to VCC or digital input 1, and this red color line, it corresponds to 0. Okay, because it is connected to ground. And here you can see there are weights, different weights. Now you might be wondering which is your LSB and which is your MSB. So you can see the branch in which current is minimum or current has the least contribution to this total current IF, it is your LSB, and the branch which has your maximum contribution, it is your MSB. Okay, so sorry, I forgot to switch on my mic also. So now if we solve this, so this will be 2 to the power n minus 2 into R plus b to the power n minus 1 VCC divided by 2 to the power, sorry, 2 to the power 1 R. Okay, so now if we solve this, so this will be V naught is equal to minus VCC by RF into R, and this will be equal to what? So this is equal to your I can write it like B naught 2 to the power n minus 1 plus B1 2 to the power n minus 2, like this till Bn minus 1 2 to the power 0. So now what I can do, I can take 2 to the power n minus 1 common. So V naught is equal to minus VCC by RF into R 2 to the power n minus 1. When I do so, so this will be B naught plus over here we will have 2 to the power 1 B1, like this. Over here we will have 2 square b to the power n minus 2, sorry, 2 to the power n minus 2 b2 plus 2 to the power n minus 1 b1. Okay, so this you can see basically now V naught is directly proportional to the values of B naught, B1, B2 till Bn minus 1. Okay, so this is what, this is your analog output, and this is your digital input. Okay, digital input. So as simple as this. But the main problem is that, can you tell me what is the disadvantage of this circuit? Advantage, you can say, sir, it's very simple, very easy to construct. Okay, very easy to construct. But what is the disadvantage? Disadvantage is that if we want to construct, suppose 4-bit DAC, sorry. So if we want to construct a 4-bit DAC, then we require resistor from 2 to the power 0R to 2 to the power 3R. Now we require 4 different types of resistor. So getting different type of resistor is little bit difficult, because in a integrated circuit, resistors are basically bulky. So the disadvantage is that multiple resistors are required, And if multiple resistors are there in the circuit, what will happen to the power? There will be huge power loss also. Okay, so that is also one more difficulty that we face, that is power loss. Okay, we face is what? We face power loss over here. Okay, so now let me ask you one question, and with the help of that you tell me what is the value of. Okay, so let me frame the question for you. Okay, so So let this be V naught. Okay, this is V1, V2, V3. This is R4. Now, if V naught is equal to, if V naught is equal to, it is equal to 3V1 plus 2V2 plus 7V3, or you can take mod V naught. Then find values of R1, R2, R3, and R4. Okay, what will be the value of R1, R2, R3, R4? So the options I am giving is option A 3 kilo ohm, option 2 kilo ohm, 1 kilo ohm, 7 kilo ohm, and 1 kilo ohm. Okay, option B, it is 1 by 4 kilo ohm, 1 by 6, 7 by 12, and 12. Option C is 4, 6, everything is in kilo ohm. Okay, 12 by 7 kilo ohm and 12 kilo ohm. Option D is 1 by 3, 1 by 2, 1 by 7, and 1 by 12 kilo. So try to find out this question. So if you see over here, if you solve the question, so pause the video, solve it yourself, and then you can watch the solution. Okay. So if you see over here, basically, if I apply basically nodal analysis at this point, so according to the concept of virtual ground, this point is 0. So 0 minus V1 by R1 plus 0 minus V2 by R2 plus 0 minus V3 by R3 plus 0 minus V0 by R4 is equal to 0. Okay, so this we get. So what is the value of V0 over here? So V0 is equal to minus V1 by R1 into R4 plus, minus, it will be minus V2 by R4 divided by R2 minus V3 into R4 divided by R3 minus, so this is V0. So V0 into, okay, so this I don't have to write. Okay, sorry. So if I take negative sign common over here, so then mod is given. So V0 mod is equal to what? It is equal to R4 by R1 into V1 plus R4 by R2 into V2 plus R4 by R3 into V3. So now look at the options and check which of the following options is correct. So over here you can see basically that R4 by R1, it is equal to what? So if you see from this equation, given equation, R4 by R1 is equal to 3. Okay. And R4 by R2 is equal to 2. And R4 by R3 is equal to 7. So which option do we see? So over here, if you see R4, this is your R4 by, so this is R4 by R3. No, this is 1 by 7. This over here, this is R4 by R3. No, even this is wrong. So look over here, R4 by R3. Yes, here it is coming out to be 7. And R4 by R2. R4 by R2 is coming out to be 2. Okay. R4 by R1 is coming out to be 3. So option C is correct. Option C is correct for this question. Okay. So then how do we basically avoid your this problem that I told you over here? Okay, disadvantage. So what we do, we then have R2R ladder type DAC. Okay, R2R ladder type DAC. Now what is this R2R ladder type DAC? So the structure is kind of same only. Only difference is that now this time we are not going to use multiple resistance. We are just single going to use two types of resistance over here. So you will see that basically only two resistors are here, R and 2R value. So this over here I am drawing one 3-bit R2R ladder logic. Okay. So this is directly connected to ground. Okay. So here also basically we have what? We have your digital inputs represented by ground and VCC respectively, corresponding to your 1 and 0. Okay. So let all this resistance value be 2R, 2R and 2R, and this is R, this is also R. Okay. And let this switch be B0, this be B1, this be B2. Now why like this, I will tell you. Okay, I will tell you why it is like this. So let us keep this as V reference, then it will be better. Okay, V reference, and this terminal is also grounded. So you can see basically that this is what? This is your 3-bit R2R DAC. Okay, R2R DAC. Now, how do we basically do the analysis of circuit? So look over here. When this B0 is equal to 1. So why I have means at the moment I am not not telling you that whether this B0 is MSB or this B2 is MSB. I am not saying, we will see it eventually. Okay. So look, when in this whole circuit, when B0 is equal to 1, okay, B0 is equal to 1, remaining all bits are 0. Bits are equal to 0. Okay. So you can see what, if remaining bits are 0, that means let this be 1 and all of them are 0 0. So what I am doing, I am just drawing this ladder logic. Okay, because this is what, this is your non-inverting amplifier. So whatever is the Vi over here, V0 will be equal to what? V0 will be equal to 1 plus Rf by Ri into Vi, means Vi is this voltage. Okay, so if we somehow are able to find this voltage, we will be able to find. So now how I find this Vi, that is the task. Okay, that is the task. So either we can use superposition theorem, that means what, bit by bit, means each switch is 1 first and then cumulatively we add everything. Okay, so like that we can do, or we can directly apply nodal analysis at this point corresponding to the input. Like if this input is 101, okay, 101. So how are we going to solve? First, we can either assume that only when this B0 is 1, get this Vi. Then as B1 is 0, so let it be, we don't have to solve for it. Then B2 is 1. So solve for Vi and then we can put it in this formula, or we apply nodal analysis at this point and get Vi. So whichever way you want to solve, you can solve it. But I am going to show you the easiest way. So that is what? That is when your each different bit have corresponding, means we are going to check one by one each of the bit. So when this B0 is equal to 1. So let us draw the diagram very quickly. So this is equal to 1 means this is connected to VCC. This is R. This is connected to ground. And even this is also connected to your ground. Okay. Now we have to find this voltage Vi1, let us assume, or this is corresponding to B0. So let us write it as Vi0. Okay. So this is 2R, this is 2R, this is R, this is 2R, this is R, this is 2R. So how do we find it? So first look, if I Thévenize the circuit from this point. So if I Thévenize the circuit, so this 2R and 2R, it is in series. So VTH will be equal to VCC by 2, and this 2R and 2R in parallel, because when I short it, okay, for calculating RTH from this point, so you can see this 2R and 2R is in parallel, so it will be R. So the equivalent circuit, if I have to draw, so it will look like this. Means I have Thévenized the circuit from this point. So this is now VCC by 2. Here we have R, okay, combination, and in series with R. So this is the R, remaining part of the circuit. So this is 2R, this is R, this is 2R, and this is Vi0. Okay. So this R and this R in series once again. So simply I am going to replace it with a single R. Okay, so this is 2R now. So now once again what we can do, basically, if you see, so I am going to Thévenize this circuit once again from this part. Okay, let us Thévenize the circuit from this part. So once again you can see, if I Thévenize it from this part, so this becomes open now. So this 2R and R, it is what? This is in your series. Okay, it is in your series. So this will be what? VTH will be VCC by 2 into 2. So that will be VCC by 2 into 2. So that will be VCC by 4. And once again, if I short it from this point, so you can see this 2R and 2R, it becomes in parallel. So that will be once again R. Okay, so this is the R. And as we have Thevenized, so this will become R once again. This is 2R. And this is VI naught. So once again, you can see that VI naught is equal to VCC by 4 into half, because this R and 2R means R and R, it will become 2R, and this 2R is in series with this 2R. So this VI naught, it becomes what? It becomes your VCC by 8. Okay. So this is your VCC by 8. Now, if suppose there were like over here, okay, let me not tell you that. So now let us do the analysis when your B1 is equal to 1. Okay, rest all the bits are then your what? It is your 1. So I am again going to take this diagram only, it will be easier. So you can see that basically now B1 is connected to VCC. So this is grounded and this is connected to VCC. Okay. So now how do we do the analysis? So you can see this R and 2R, it is in. So I should write also B1 is equal to 1, remaining all bit 0. So this R, 2R, 2R, it is in parallel. So basically this will become R. Okay. This will become R. And this R and R, it is in series. So I can replace it with 2R. So once again, if I Thevenize the circuit from this point, so what will happen? So this will be VCC by 2. This is the R. Why? Because if I short it once again, so this 2R and 2R, it will be what? It will be in your parallel. So 2R, 2R parallel is R. And we have this R also. And this is the 2R. And let this time it be VI1 because it is due to B1 connected to VCC. So this will be VI1. So now you can see VI1 is equal to VCC by 2 into half. So that is VCC by 4. Okay, VCC by 4. Now the last case is when I connect B2 equal to 1. Okay, if I connect B2 equal to 1, then what will happen? This is VCC now. So you can see if I start Thevenizing or just simplifying the circuit, so this 2R and 2R, it is in parallel, so I can convert it to a single series R element. Okay, see very carefully. So this is the single R. Now this R and this R, it is once again in series, so I can remove it and write a single 2R. Now once again see this 2R, 2R, it is in parallel, so I can remove it and simply write R over here. And now you can see this 2R and this R plus R means 2R, it is in series. So VI2, it comes out to be what? VCC by 2. Now, why did I say when I started this analysis that this bit is MSB and this bit is LSB. Now you can see when this bit is on, the corresponding voltage is VCC by 8, but when this bit is on, it is VCC by 2. So which has more value of voltage? This bit. So that is why this is MSB and this is LSB. Now if suppose there were like this n bit, so what would have happened? See, here it was 3 bit, so that is why we got VCC by 8. If there was n bit, we would have got VCC by 2 to the power n. Okay, VCC by 2 to the power n. Sorry, I have written VCC over here everywhere. It should have been V reference because I have taken V reference. So this is Vref by 2, Vref by 8. So this will be Vref by 2 to the power n. Okay, any doubt in this up to this point? So now what do I get over here? This value of Vi. This Vi I told that I am going to apply. So Vi is equal to, now let us do the analysis. Vi is equal to, so what did I take every place? Vi2. Okay. So Vi naught plus Vi1 plus Vi2. So Vi1 is Vref by 8. This is Vref by 4 plus Vref by 2. Okay, this we got. Or if I take Vref by 8 common, so this will be 1 plus 2 to the power 1 plus 2 square. Okay, this value we got. This value we got for Vref. Okay, fine. So now what I told you, as this is your non-inverting amplifier, so Vout is Vi into 1 plus Rf by Ri. Go back to the circuit diagram. Rf by Ri. So now if we write, so that will be what? That will be equal to Vout is equal to Vi is Vref by 8 1 plus 2 to the power 1 plus 2 to the power 2 1 plus Rf by Ri. Okay, so is it clear? Now if I want to write generalized way in terms of switches, okay, generalized for n bit, okay, for n bit. So how am I going to write? Vout is equal to, look, Vref by 2 to the power n. Okay, 2 to the power n 1 plus, okay, 1, or I can even write it, means I can write it like this, 1 plus 2 to the power 1 till 2 to the power n minus 1, 1 plus Rf by Ri. But one thing to note is that I have considered that all the bits are 1. Okay, all the bits are 1. Now if I want to write in terms of switch, now few of the switch might be, it might be connected to this 0. Okay, here I have considered all the switch are connected to this red color. Okay, but some of them might be connected to 0 also then. So we have to write it in terms of general switch also. So then what we do? So then we are going to write Vref by 2 to the power n. See, now this time I am going to write B naught 2 to the power 0 plus B1 2 to the power 1, like this. Bn minus 1 2 to the power n minus 1 1 plus Rf by Ri. So this is what? This is your basically the formula for your R2R ladder type DAC. Okay, R2R ladder type DAC. Now you can even write it like this in summation form. Vref 2 to the power n, and summate this from I equal to 0 to n minus 1 bi 2 to the power I. Okay, bi 2 to the power I 1 plus rf by ri. Okay, so I shouldn't be writing I over here. Let me write something else. So let this be j. So this is bj 2i to the power 2 to the power j. Okay, so this is what? This is your basically R2R ladder type DAC. Okay, so this too, it is specifically asked in GATE exam. Okay, none other is asked because there are even R2R ladder using non-inverting op-amp also. Okay, non-inverting op-amp is also there, but it is not required because that is not asked in the examination. Okay, so now let us see few more points. Okay, few more points. What is that? What is the full scale output voltage of DAC? Okay, what is full scale output voltage of DAC? Let us try to see. See, basically the full scale output voltage of DAC is the voltage of the DAC when all the bits are actually 1. Okay, when all the bits are actually 1. So let us write full scale output voltage is full scale output voltage is the maximum value possible of the DAC, or what you can say, the output of DAC corresponding to the maximum digital input. That means what? If we have one 3-bit DAC, so the maximum number that we can write using 3-bit digital input is 111. So what is the corresponding analog output? Okay, so that is what full scale DAC. Now what should be the case over here? That all the bits should be equal to 1 when calculating full scale output voltage. So right, all the bits of input in the DAC should be equal to 1. Okay, all the bits of input in the DAC should be set to 1. Like for example, if we have a 4-bit DAC, then what should we write? All the switches like B3, B2, B1, B0, it should be equal to 1, 1, 1, 1. Okay, it should be equal to 1. So now, what are the number of steps in any n-bit DAC? So this is one important concept. Number of step in n-bit DAC. So usually students make mistake in this. So if suppose I have a 1-bit DAC, so look, 1-bit DAC. So what are the possible values? Either it can be 0 or it can be 1. So how many steps can you see? You can see basically there are only one step. Okay, one step is there. Now if suppose we have what? We have 2-bit. So for 2-bit, how many steps are we going to have? So this is 0 0, this is 0 1, this is 1 1, sorry, this is 1 0, and this is 1 1. So the number of steps that we have over here is what? 1, 2, and 3. So 3 steps. Similarly, if it is 3-bit, then how many steps we are going to have? So it will be 0 0 0 0 0 0 1 0 1 0 0 1 1 1 0 0 1 0 1 1 1 0 1 1 1. So how many steps you can see? 1 2 3 4 5 6 7. So there are basically 7 steps. Okay, step change, these are known as step change. So basically number of step for n bit DAC, it will be how many? It will be 2 to the power n minus 1. Okay, 2 to the power n minus 1. Put the value of n like over here. So that will be 2 minus 1, 1. Here it will be 2 square minus 1. So that is 3. 2 cube minus 1. So that will be 7. So these are what? These are your number of step changes. So here you can see basically this number of steps means the number of transition or simply the number of edges that in a DAC we will encounter. What did I say? This number of step means number of transition, okay, number of transitions or transitions or number of edges. Okay, number of edges. Now one more quantity that we need to define is your step size. Step size. Now what is the step size? So step size is defined as the increase in analog output when there is a single change in your digital output. So what did I say? Step change is the increase in analog output when there is a single change in digital output. Okay, so basically that means what? If suppose I have a 3-bit DAC, okay, if I have a 3-bit DAC, then step size is basically the voltage change when I move from either 0 to 1 or from 1 to 0, okay, sorry, 1 to 2 or from 2 to 3 or from 3 to 4. So these are what? These are the analog corresponding difference between the two consecutive steps is known as step change. Okay, it is known as step change. Or sometimes this step size is defined for only the output of this one. Okay, output of this value is told as what? It is known as step size. Why? Because you can see for 0 0 0, that means no input to your DAC, it should correspond to 0 volt. So for the minimum or the least change in DAC, the output we get, it is known as step size. So we can write also the least change in DAC for which we get output is called step size. Okay, it is called step size. That is for 0001 or for 0001 if it is your 3-bit DAC. Okay. So now what is this full scale output voltage? Full scale output voltage. So full scale output voltage is what? It is the max voltage of DAC. Okay, max voltage of DAC, or when all the bits are 1. When all the bits are equal to 1, then we call it as what? We call it as full scale output voltage. So that is equal to step size into number of steps. Okay, step size into number of steps. So what is step size? Step size is the voltage corresponding to a single step. Voltage corresponding to a what? To a one step change or to a single step change. And what is number of steps? Number of steps means what? Basically it is 2 to the power n minus 1. Just now we saw. Okay. So this is what is your full scale output voltage. Okay. So the next concept that we have to see, it is the resolution of DAC. Okay. Now what do we mean by resolution of DAC? So it is the minimum increment in output that DAC can indicate. Okay. So it is basically what? It is the minimum increment in output that your DAC can indicate. Okay, so just now we have seen what? Full scale output voltage is equal to number of step size into number of step. So basically resolution is what? Resolution is basically the voltage that is indicated by your 001 or 0001. So here you can see basically it corresponds to your digital input 1 divided by the total number of steps, that is equal to what? 2 to the power n minus 1. So what do we get? Basically we are getting the output voltage for our first bit. Okay, so this is known as what? This is known as the resolution of your DAC. Okay, resolution of your DAC. So with this we actually end the DAC part. So in the next session we are going to cover ADC, and after ADC we are going to solve questions of this topic. Okay, is it clear? So if you guys have any doubt, you can post in the group that we are. Okay, Okay then, see you in the next session.